Okay, now let's continue with our topic of today. Actually, this topic, fuzzy reasoning, will keep us busy, definitely this class and also the class of next week. So what are we going to discuss here? We are going to discuss how fuzzy rules work, and we will learn about methods of fuzzy reasoning, and we will look closer at two methods, the so-called direct method and the simplified method. Now, but first, let's look at what's a rule. In logic or in logical reasoning or in rule-based systems, a rule is normally written in the form if A, then B, where A is some statement and B is also some statement, where the A is called the premise or hypothesis or also antecedent, and B is called the conclusion or the consequence. An example of such a rule could be, if it rains, then I get wet. So it rains is a statement, and I get wet is another statement. So the premise or hypothesis is it rains, and the conclusion is I get wet. So this is the way how rules are normally formalized. And the same way it works also in fuzzy based systems. We will discuss that in a minute. So these are the rules. And reasoning means, in logical reasoning, we apply a set of rules and given data or given facts. And the application of this data or the facts to the rules using rules of inference or so-called logical rules produce conclusions. So the reasoning in formal logic looks like that. We have rules and we have given facts. So we apply the facts to the rules and we use logical inference, so-called rules of inference. And then if we can come to the conclusion, we say that this argument is valid. Or we come to some other conclusions where we know that the argument is not valid. So in reasoning, we have two basic rules of inference, two very fundamental, simple rules of inference. In our binary logic, where we have only true or false, we have two rules of inference, and they are called deduction and induction. The deduction also is called modus ponens. That's a Latin expression. And the induction is called modus tollens. So in the literature, you might find these two terms also. The first one is the principle of deduction, which works in this way. If X is A, then Y is B. Just, sorry. Just trying to get my pointer. Okay, here it is. So the deduction principle or the modus ponens works in that way. If X is A, then Y is B. X is A, therefore Y is B. And in the other, more or less the other way around, the induction principle works in that way that says if X is A, then Y is B. Y is not B, therefore X is not A. So we will see that later on in our rule-based systems, we always use this deduction principle. So let's look at a very simple example. For the deduction principle, we have the rule, the premise, if it rains, then I get wet. Premise number two, it rains, therefore the conclusion, I get wet. So it's a very simple logical rule. And in the induction principle, this would read like that. If it rains, then I get wet. That's our premise. I do not get wet. Therefore, it does not rain. So this these two principles. And in fuzzy reasoning, we use the same principle, but we call it a generalized modus ponens, or a generalized deduction principle. So we have again a premise: if x is A, then y is B. Then x is A dash here, and y is B dash, meaning that A and B and A dash and B dash are fuzzy sets where they are not exactly the same, or in other words, they are similar. Let's look at an example here. If we say if the temperature is low, then set the heater to high, where low and high are fuzzy concepts. Now, the premise number 2 would be the temperature is very low, where you see that's a modification, not exactly the same as our value here. And the conclusion is then set the heater to very high. So this is the generalized version of this modus ponens. And that's what we are going to use throughout our examples here that we are also later on looking at. Now, we know 3 simple methods in fuzzy reasoning, so-called direct methods, and there are 3 types of them. The first one is called Mamdani's direct method. The second one is called Tagaki and Sugeno's fuzzy modeling, and the third one is called the simplified method. I will show you, on the next slides how the rules are formulated using these 3 approaches to direct methods. In our practical examples, we will only use Mamdani's direct method and the simplified method. And we will also use the simplified method later on in our class for geodata, where we will implement a fuzzy reasoning problem with geodata using the simplified method. So that will come later in this course, towards the end of the course, when we have the practical examples. Now let's look at how are the rules formulated in Mamdani's direct method. A rule is formulated in such a way: if x is A and y is B, then z is C. So we have here A, B, and C are fuzzy sets, and x and y in the premise are called premise variables, and the z in the consequence or in the conclusion is called the consequence variable. So this is the most general form of a fuzzy rule. And if we look at an example, it can look like that. If room temperature is high and humidity is fairly high, then set the air conditioner to high. So what we see here is we have high, fairly high, and high are fuzzy sets. The first one for temperature, for high temperature, and the other one for humidity, and for the setting of the air conditioner. So we have 3 fuzzy sets, and where we have temperature, humidity, and air conditioner setting as premise and consequence variables, respectively. So this is the most general form of formulating a fuzzy rule in Mamdani's direct method. I said there is a second way, which is called Tagaki and Sugeno's fuzzy modeling. The rule on the premise side looks exactly the same. If x is A and y is B, then z is a linear function of the premise variables. So it is the difference is that the conclusion is not, as in our case, a fuzzy set, but it is a function of the variables. An example could be, again, with the same example that we used before. If the room temperature is high and humidity is fairly high, then set the air conditioner to a function of room temperature and humidity. So that would be the second approach. And the third one, the simplified method, and you will see here why it's called simplified. Of course, the premise is the same. If x is a and y is b, then z is equal c. So the conclusion has nothing fuzzy in it anymore. The conclusion is a so-called fuzzy singleton. It is just a value, a real value. So on the conclusion side, we have no fuzzy expressions anymore. So again, jumping back for a moment, the most general form of the direct method has in the conclusion a fuzzy set. The fuzzy modeling, according to Tagaki and Sugeno, has in the conclusion a linear function of the variables, and the simplified method has in the conclusion a single real value. So that's why it's called the simplified method. So there's nothing fuzzy in the conclusion anymore. Like in this example, if the room temperature is high and the humidity is fairly high, then set the air conditioner to 9, some absolute value setting. So this means this is an example for the simplified method. Now, we have shown here rules with two variables in the premise, a and b as fuzzy sets and x and y as the premise variables, but we can of course also use less or more variables. On the next slides, I show you an example. This is an example with just one premise variable. So the general form looks like if x is a1, then y is b1. If x is a2, then y is b2, and so on. There can be a lot of rules. And then we have x is a and y is b, meaning then we have given values for x, giving us a conclusion value for b. And the general form, again, you can see here is this generalized modus ponens, where here P implies Q is the part of the rules, the premise rules, then the given values, and then the conclusion follows. So here is a very simple case with just one premise variable. On the next slide, we have two premise variables as we had in our examples before. If x is a and y is b, then z is c, and so on. As you can see here, the number of rules is arbitrary, so it depends on your system, on your model, how many rules you have, and of course, whether the rules make sense or not is up to some expert knowledge. And that's also the way how rules are normally implemented, that they come from the knowledge of some experts or some expertise. So again, here the rules with our two premise variables, x and y, then given values, or the data, as we said in the introduction, the given data for x and for y, and applying the rules to these given data, we come to a conclusion. And the most general form, of course, is when we use an arbitrary number of premise variables. So from, let's say, from x1 to xm, then our rules would read like if x is a, if x1 is a1 and x2 is a2 and xm is am, and so forth. And of course, then we would also need given data for our m premise variables, and they applied to the rules would give us a conclusion. And as we know from the Mamdani's direct method, the conclusion is also a fuzzy set B. So in the next slide, I will give you a kind of a procedure, or if you wish, a kind of a cookbook, how we can apply Mamdani's direct method to a given set of rules, how it works. So on this slide, you have in 4 steps the procedure how to do that. Of course, what we need to have is we need to have a set of rules with a certain number of premise variables, and then we can follow the procedure in 4 steps. In step number 1, we would apply the input values, meaning the given values for our premise variables. So we would apply the input values to the premise variables for every rule and compute the minimum. So what we would do is we have given values. For example, here we have an example of 2 premise variables. For simplicity, I took here 2 premise variables, x0 and y0. Oh, sorry, x and y. And then we have given values x0 and y0. So we would have, in every rule, we have to enter the values into the membership function for our premise fuzzy sets. So for set A1, it would give a certain membership value for x0. And in the set B1, it would also give a certain membership value for the y0. So we have 2 membership values, and of these 2, we take the minimum, which is our M1. And we do that for every rule. So here we have n rules, so we do that n times, always entering the given values into the rule, into the premise part of the rule, and compute the minimum. So in this first step, we end up with n values for every single rule. So for every rule, we get 1 value, which is the M1, M2, up to Mn. So these are those minima that we compute here. That's the first step. Then, in the second step, we have to take these minima per rule and cut the membership function of the consequence at that respective value. So for rule number 1, we have a rule that reads if A and B, then C. So we for the A and B, we already had the minimum, which is our M1, and we take this M1 and cut the membership function of the conclusion of our rule number 1 at that M1 value, and we do that for every rule. So if we have n rules, we do that n times, and we end up with n of these values, or I should say with n of these truncated membership functions of the conclusion. Don't worry, I will just show you an example in a few minutes, and then it will become very clear. And if you look at the examples later on and you come back to that slide, you should understand what I just explained to you. So in step 1, we compute the minima for every premise part of our rules. In step 2, we cut every conclusion fuzzy set at these minima for every rule. And in step 3, we take this cut or truncated membership functions for the conclusion of every rule and compute the union of all these. So what you see here is I use the maximum operator here for computing the union. If you remember when we were discussing union and intersection of fuzzy sets, I explained to you that there are several operators for union and intersection. For example, for the intersection, we can use the minimum operator. And for the union, we can use the maximum operator. So in this case here, we use the maximum operator to compute the union of all our resulting conclusion sets, of all our truncated conclusion sets, which gives us a fuzzy set in the end. But what we would like to have is we would like to have a single value as a result, because that's already our result in step 3, but the result is a fuzzy set. So we would like to have a single value, and to compute such a single value, we apply a defuzzification to our fuzzy, to our conclusion fuzzy set. And the defuzzification can be done in different ways. We use here the so-called center of area method by computing the final value as the sum of all our membership values in the conclusion multiplied by the value divided by the sum of the membership values. So again, in a minute, you will see what I exactly mean with that. So let us now just look how that works for an arbitrary number of premise variables. Of course, then our rules look like this. We have m premise variables and 1 conclusion variable. So we would compute the minima. Here I indicate this minimum by intersection with the minimum operator. That's exactly what we did here. Actually, what we did here is we computed the intersection of these 2 premise fuzzy sets for the given data. And this intersection was computed using the minimum operator. So we use the minimum operator here in step number 1, which gives us all those minima. Then we cut the conclusion fuzzy sets for every single rule at that given minimum value, again using the intersection as the operator to cut these conclusion fuzzy sets. So we do that again for every single rule. And then in the end, we compute the union of all those cut conclusion functions, conclusion fuzzy sets using the maximum operator for the union. As you can see here, we used the maximum operator for computing that union. And then finally, we defuzzify our result with the defuzzification operator as explained before. I am going to show you a concrete example with this direct method. Again, recall the procedure. Consists of 4 steps. First, compute, I simplify now. First, compute the minima. Step 2, cut the conclusion functions at those minima. Step 3, compute the union of the resulting conclusion functions of these cut conclusion functions. And step 4, defuzzify the result. Now, let's look at one particular example. Let's assume we have 4 rules, and this example has nothing to do with geodata. It's just taken from everyday life, driving, and perhaps the rules don't make much sense, but it is just for the sake of simplicity and giving you an idea how that can work. So we have 4 rules. we have rule number 1 that says if the and in fact what do we have as premise variables? We have distance between cars and speed of the cars, and the conclusion variable is something about acceleration or deceleration, whether you should increase the speed, reduce the speed, or maintain the speed. So we have 3 linguistic variables: distance, speed, and the acceleration or deceleration behavior. And we have values for these variables. For distance, we have short and long distance. For the speed, we have low and high speed. And for the acceleration, deceleration, we have 3 values: reduce speed, maintain speed, and increase speed. So with these variables, we have now 4 rules. Rule number 1 says if the distance between the cars is short and the speed is low, then maintain the speed. Rule number 2 is if the distance between the cars is short and the speed is high, then reduce the speed. Rule number 3 said if the distance between cars is long and the speed is low, then increase the speed. And rule number 4 says if the distance between cars is long and the speed is high, then maintain the speed. So what you see here is these are all fuzzy concepts: short, high, long, low, maintain, reduce, increase speed. These are all fuzzy concepts. So we have here a set of fuzzy rules, and we want to see what's the conclusion with given data for distance and speed. So if we have the given distance between cars and the given speed, what will be the conclusion according to these 4 rules? So first, we need membership functions for our values of the linguistic variables. So first, we need membership functions for the values for the variable distance and the values short and long. Now, here are the 2 membership functions for short distance. I defined it in such a way that I say if the distance is less than 10, the distance is definitely short. Then between 10 and 30, the membership value decreases and becomes 0 at 30 and beyond. So that would be the membership function for short distance. The membership function for long distance is more or less the complement, but I defined it here again with a formula. I said it's 0 up to 10 meter distance, then the membership value increases up to 30, and from 30 on it stays 1. The membership to long distance stays 1. You see here the formula according to a linear membership function for short and long distance. Of course, it depends on the circumstances, on the model assumptions, on the knowledge, how you define these membership values. So I just defined it in this way. Perhaps the distance of 30 meters between cars is pretty short. It should be more, but it's just for the simplicity of this example. Now, this would be the membership functions for distance, and 2 values, short and long. Now we need the membership functions for the speed. And again, for speed, we had 2 values, low speed and high speed. So we define it here in such a way that I say low speed, everything below 30 kilometers per hour is definitely low speed with a membership value of 1. Then the membership value to low speed decreases and becomes 0 at 70 kilometers per hour. So at 70 kilometers per hour, the speed definitely is not low anymore. And there on, the faster you go, it stays 0. And on the other hand, I define the membership function for high speed in such a way that I say, well, up to 30 kilometers per hour, the speed is definitely not high. So the membership value is 0. Then it increases, becomes 1 at 70 kilometers per hour. And from 70 kilometers per hour on, it stays 1. So from there on, the membership to high speed is definitely 1. Again, you could define the membership functions in a different way. That doesn't matter. It just will change the resulting values. So we have now the membership functions for our premise variables, distance and speed. Now we need the membership functions for our acceleration, deceleration behavior. Here you remember we had 3 values: brake, meaning reduce speed, keep speed, and accelerate, increase speed. So for braking, we define for a value less than -10, it is 1, meaning the higher the negative values, the stronger we brake. So reduce the speed up to -10 is definitely a strong deceleration or braking very hard. Then the membership value decreases. At 0, it becomes 0, meaning the 0 value means we do not change our speed, we do not decrease it, we do not increase it, we just maintain it. So, and from there on, it stays 0 because we definitely do not brake anymore. For the acceleration, we say up to 0. And remember, the negative side is the braking side. So for acceleration up to 0, meaning maintaining the speed, we definitely do not brake. We definitely do not accelerate because we are on the brake side here. Then the membership value increases at the +10, it becomes 1, meaning between 0 and 10, the membership to acceleration increases, and from 10 on it stays 1. And for maintaining the speed has the membership value of 1 at 0, because at 0 there's no deceleration, there is no acceleration. And the more we brake or the more we accelerate, the lower the membership value becomes to maintain the speed. And at -10, less than -10 and more than +10, it remains 0. So this would be our 3 membership functions for the 3 values: decelerate, keep speed, and accelerate. So now we have our membership functions for all our variables, and now we can take data, given data for distance and speed, and see what happens. Well, let's for this example take a distance of 15 and a speed of 60. Now, in step 1, you remember in step 1 we said, I just jump back to our, sorry, that was too far. In step 1, we apply our given values to the premise variables and compute the minima. So what does it mean here? In step 1, we have to take distance 15 and speed 60 and start at rule number 1. So rule number 1 said distance short, speed low. So we have to apply distance of 15 to short. Short distance, 15. So we end up with a value somewhere here, 0.25 or something like that. So in fact, short distance. I was looking at the wrong. Short distance is here. There's the red line, and 15. Then we are here, somewhere at this point, and that is a value of 0.75. So for short distance, we get a membership value of 0.75, and for speed 60 at low speed, we get a membership's value of 0.25. So again, let's look with speed 60 and look at our low speed, 60. Low speed is the red line, so gives us a value of 0.25. So this would be for rule number 1, and the minimum of these two is of course 0.25. The same way we do for short. Rule number 2 says short distance, high speed. So again, with the value of 15, we go into short distance, giving us the membership degree of 0.75. And then with the speed of 60, we go into the membership function for high speed, which gives us a membership value of 0.75. So high speed with 60, high speed is the blue line, 60, high speed, then we are somewhere here, giving us a membership value of 0.75. And again, the minimum of these two is 0.75. Then rule number 3 says long distance and low speed. So if the distance is long and the speed is low, again with value of 15 for speed, 15 for distance, we go into the membership function for long distance with a distance of 15, giving a membership value of 0.25. And then with the speed of 60, we go into the membership function for low speed. And again, this gives us a value of 0.25 because rule number 3 says long distance, low speed. So the minimum of these two, of course, is 0.25. And rule number 4 said is the distance is long and the speed is high. Again, we go with 15 into the distance for long distance, giving us a membership value of 0.25. And then with the speed of 60 into the membership function for high speed, giving us a membership of 0.75. So the minimum of these two is 0.25. So now we have completed step number 1. Step number 1, you remember, is enter the given values into the premise variables of our rules for every rule and compute the minimum of these values for every rule. So we have 4 rules. For rule number 1, the minimum is 0.25. For rule number 2, the minimum is 0.75. For rule number 3, the minimum is 0.25. And for rule number 4, the minimum is also 0.25. Now, step number 2 says, take these minima for every rule and cut the corresponding conclusion membership function at this minimum. So this is our rule number 1, conclusion. So the conclusion of rule number 1, let's say, is maintain speed. That's the conclusion for rule number 1. The maintain speed membership function is this triangular function here, the green one. So this is our maintain speed. And remember, the minimum of rule number 1 was 0.25. So we take this maintain speed membership function and cut it at 0.25. So this is now the truncated or cut conclusion membership function. Rule number 2 had as a conclusion reduce speed. Let me jump back. Reduce speed. So reduce speed membership function or reduce speed or break looks like that. And the minimum was 0.75 for rule number 2. So we cut it at 0.75, giving this blue line. Rule number 3 said increase the speed. And the minimum was 0.25. So we cut this increase speed at 0.25, giving this blue line. And rule number 4 said maintain the speed. And the minimum was also 0.25. So we cut at 0.25. So we have now completed step number 2. Remember, step number 2, take the minima of step number 1 for every rule and cut the conclusion membership function at the corresponding minima for every rule. And that's what we did here, giving us this as a result. So these are the cut conclusion membership functions. And then step number 3 says, now take all these conclusion membership functions and compute the union of all these. So we take all our conclusion membership functions, that put them together and compute the union, which looks like this. So you see here, this is now a fuzzy set. And in step number 4, we say we have to defuzzify our result. So we want a single value, and we do that. There are several methods of doing it. We are doing it with this center of gravity method, giving us one single point, which is more or less, let's say, the central point of this fuzzy set. And in our particular case, it would give us this a point here with a value of minus 5.45, which would be here. So that is more or less the gravity point of our membership function, so the center of area approach. And minus 5.4 means reduce the speed a little bit or break a little bit. So with the given rules and a speed of 15, a distance of 15 and a speed of 60, the conclusion is break slightly. So that is the example for our fuzzy reasoning, using this example with the cars, using the direct method of Mamdani. So as you can see here, it's pretty straightforward. And in fact, I also have prepared a spreadsheet, which I will show you. I have prepared a spreadsheet with that particular example. Again, I will share these spreadsheets later on again with you. For the time being, on the website, which I show here, you only have the slides of today's class, or let's say you have the slides for fuzzy reasoning. So there are all the slides with regard to fuzzy reasoning. And I'm not quite sure if we will need all the class of today, and definitely we will need all the class of today, but I'm not sure whether we will need all the class of next week for fuzzy reasoning. So it might be that next week already I will start with the next topic, generation of fuzzy sets in GIS. So I'm not sure, depends how fast or how slow we progress in our class. So later on today, you will find here the recording of today's class, and you will also find the spreadsheet of these examples. So let me jump back to our example here. What do we have? We have the same problem that we discussed before. we have short distance, long distance. Let me see, maybe perhaps I make it a little bit bigger that you can. If you have a smaller screen, then maybe it's easier to look at the magnified picture. Let me see how fast. Okay, that should do it. So again, here our membership functions for short distance, long distance, which is implemented here using using the if statement in Excel. So by the way, by the time now you should be familiar with that if statement, because it basically always works in the same way. So for short distance, for long distance also, implementing this function here. So and what we have here is then a graphic representation of short distance, as you saw in the slides, and for long distance, as you will find also on the slides. So this is our membership functions for distance. Then we have the membership function for speed. Again, where we have two values, low speed and high speed. The low speed defined as we have on the slides. Again, here you have the membership function, and here you have the membership function for high speed, giving you the graphic representation of the membership function for low speed and for high speed. So both together. And finally, we have the membership function for the acceleration or deceleration, given with these three membership functions: brake, accelerate, and keep the speed, as we had defined it on the slides. Again, here converted to our if statement in Excel, pretty straightforward, giving you the membership function for brake, decrease the speed, which looks like that, increase the speed, which looks like this, and keep the speed, which is this triangular function. Now, let's show them all together. Fine. And now we said we have, as an example, a distance of 15 and a speed of 60. Now, let's see what how we proceed with that. So what we do is we first have to apply these values to our premise variable. So this is the step one. Apply it to the premises and compute the minima. So in other words, we have to apply distance. And again, we have to recall our rules, of course. The rules were in rule number 1, short distance, low speed. So we have to go with 15 into the short distance. The short distance, you see here, short distance with a value of 15 gives us 0.75, and the speed of 60 with low speed, a membership value of 0.25. So that's what we do here. We take the values for distance and speed, the membership values, and compute the minimum. Minimum very, very easily with the minimum function in Excel. And we do that for every rule. So we do that for the rule number 2, with 15 and low speed, with 60 and high speed. The minimum gives this. Then for 15 with short distance, with a long distance, and with 60 for high speed, gives these two values the minima. And for rule number 4, we compute here again the minima. Now we have all those minima. And then you recall that in the next step, what we have to do is we have to cut the conclusion functions at those minima. And we have to do that for every rule. So we have here the universe for our conclusions from -20 to +20. You recall this was our diagram from -20 to +20, from brake hard to maintain speed to accelerate strongly. And we apply our cutting here by computing the minimum of the conclusion value with the minimum that we calculated in our step number 1. So we take the conclusion value, for example, for -20, and I did this here in this table in steps of 5. Yeah? Of course, I could use finer steps, but then the table gets longer and this whole thing gets a little bit more confusing. So it is just for illustration purposes, I used steps of 5 here. So you see from -20, -15, -10. Of course, I could have used finer steps too. So for rule number 1, we have to take those minima, cut the membership function of the conclusion at the corresponding minimum, which I'm doing here in this. And I do it for rule number 1, for rule number 2, for rule number 3, and rule number 4. So we have to do that for every rule. I do it here. And then we have to compute the union, which I do here. And for the union, I use the maximum operator, giving us these values here. So this is our step number 3, basically, which gives us in general gives us a conclusion membership function, and then we still need the final step of computing, of doing the defalsification. And the defalsification we do according to just going back here. So the defalsification we do according to this formula here. Taking these union values, the sum of these unions multiplied with the value divided by the sum. And this is what I'm doing here. Here in this step, I calculate this multiplication. And here in the end, I take the sum of these, which is the multiplication of the union value times the given conclusion value divided by the sum of this, which you can see here in this. So as I said, I will make this spreadsheet later on available to you, so you can study it more closely and you can play with it. So actually we can now play with it as you see, it gives us a conclusion value of minus 5.9. And we can, for example, change the values here and see what happens. So if we increase the distance, let's say we have a distance of 30 and a speed of 60, what changes? Well, the result changes to that the conclusion value, the defalsified conclusion value is 4.5, meaning we can increase the speed because we have a relatively high distance. And if we reduce the speed here even more, let's say reduce it to 40, we can even stronger accelerate according to our rules. On the other hand, if we have a distance, let's say, of 40 and the speed of 40, doesn't change anything here, but the speed of 60, let's say, or 70, distance of 40 and the speed of 70, we could maintain the speed. If the distance reduces to 30, and the speed of 70 means maintain the speed. If we have a very short distance and a very high speed, brake very strongly. So you can see here, you can play with that spreadsheet. And this is the a simple implementation in Excel of Mamdani's direct method, where I can jump back to this slide that runs in 4 steps. The major point here is that in step number 3, the conclusion that you reach is a fuzzy set, which you have to defalsify to end up with one single value. And this is our step number 4. When we go now to, okay, we have done this example. If we now look at the simplified method, the simplified method, you remember, the simplified method is based on rules that have a number, a so-called fuzzy singleton, a real number in the conclusion. So in the conclusion, there is nothing fuzzy. This reduces our steps to 3 because we do not get as the conclusions in step number 2, we do not get fuzzy sets. In step number 2, we already get values. So that reduces our approach, or our, you could say, our algorithm or our recipe to 3 steps only. Step number 1 is exactly the same as it was in Mamdani's method. So in step number 1, we take the values, the given values, apply them to the premises, and compute the minima for every single rule. So it's exactly the same as in step number, as with Mamdani's method. In step number 2, you remember in Mamdani's method, in step number 2, we were cutting the conclusion fuzzy sets at those minima for every single rule. Here, in step number 2, we do not need to cut any fuzzy set because the conclusion is already a single value. So the only thing we need to do is, in step number 2, we need to multiply the minima with the conclusion values to come to the conclusion of every rule. So to take the minimum of rule number 1 and multiply it with the conclusion value of rule number 1 gives us the conclusion of rule number 1. And we do that again for every single rule, giving us these conclusion values. And then we compute the final conclusion as the sum of these conclusion values divided by the sum of the minima. And again, this is a very straightforward approach. I have to check, I think I have this also in, do I have that? And yes, I have this also with the simplified method, the same example that we had before. So let me make it a little bit bigger. Again, there's nothing new here. The membership functions for short distance, long distance, and for speed, low and high. There's no difference. These are the same membership functions as we had before. Only now we have conclusion values here. You remember this is now the simplified version, so that means our rules must read differently. When we had first our rules here, rule number 1 had, sorry, that's the wrong example. Is it? So this one, in our rule number 1, it says maintain speed. Okay, now we translate maintain speed into a real number, 0. You remember when we had the fuzzy set for acceleration or deceleration at the value 0, we had a membership of 1 to maintain the speed. So we take 0 here as the conclusion value. Rule number 2 said reduce the speed. So we translate reduce speed into -5, which is let's say a kind of normal braking. Rule number 3 said increase the speed. We translate increase the speed to a value of +5. And rule number 4 said maintain the speed, and we translate this maintain the speed again into a value of 0. So we have now here for rule 1, 2, 3, and 4 conclusion values. There's no fuzzy set anymore, which simplifies our calculation. In the first step, again, we take 15 as a distance as an example and 60 as a speed. And in the first step, we have to compute the minima, which we do here. So we enter our given distance and our given speed into every rule and compute the membership values to distance and speed, which are these. For distance, we get these values. For speed, we get these values. And of course, then we take the minimum of these corresponding values, which gives us this. And now we can already compute the conclusion values in step number 2. Step number 2 was, as you can see here, step number 2 is take the minima for every rule and multiply them with the corresponding conclusion value. So that's what we do here. We have our minimum. We have here the conclusion value for rule number 1, which is 0. For rule number 2 is -5. For rule number 3 is +5. For rule number 4 is 0. And we compute the multiplication of these two. So we multiply the minimum with the conclusion value, which gives us these corresponding values here in the conclusion part. Now, for the final conclusion, we said, the only thing we need to do is calculate the sum of these conclusion values divided by the sum of the minima. So the sum of these conclusion values divided by the sum of the minima, which we do here. As you can see here, the sum of the conclusion values divided by the sum of those minima, giving us, in this particular case, -1.7 roughly. So this is the simplified method. And what you can see here is, of course, it's not exactly the same values as we had what did we have, 15 and 60 in Mamdani's method. In Mamdani's method, we had minus 5.9. Here we get minus 1.7. That depends, of course, on the choice of our conclusion values here. If I would choose different conclusion values here, then I would also get different results. But again, we can play here. We could say, what is if the distance is higher? Then you see that we get a slight acceleration value. If the speed is also low, we get an even higher acceleration value, and so forth. So what you see here is that we have the simplified method, which is relatively easy to compute, because in the conclusion side, you do not have fuzzy sets, and you do not need to apply this defuzzification process. So later on in this course, what we will do is we will do one concrete example with geodata in a GIS, and we will use one reasoning example using this simplified method. And again, as I said before, if we choose different conclusion values here, for example, if I would choose, let's say, minus 3 here and here plus 3, then the values again would change. Or if I use minus 6 and plus 6 for decrease and increase the speed, of course, the conclusion values also change. So depending on your rules, of course, the rules consist of the premise and the conclusion part. The final result of such a fuzzy rule system will, of course, also change. So it is very important to choose the rules properly, depending on your expert knowledge or some other expert input, because the whole thing depends on how good you have chosen these these rules. Okay, so we are basically at the end of our class of today.